So for our first one here, I'm going to show you one of the kind of conventions or tools that we always use when we're talking about vector quantities. Because obviously if we're looking for displacement, we're solving for something that's a vector quantity in this question. Okay? So what we generally do is we draw vectors, or we represent vector quantities with arrows. The magnitude of the arrow represents, or sorry, the length of the arrow represents the magnitude of that particular value. And then we just point the arrow in whatever direction that particular vector is going. Okay, so for our first one here, okay, we got these sprinting drills that include running 40 meters north, walking 20 meters north, and then sprinting 100 meters north. This question has nothing to do with how fast they're going at all, does it? Just how far and in what direction, because it's displacement. So all I do is go, okay, my first vector is 40 meters north. Okay, and then my next vector is 20 meters north. Okay, so you can see that that second arrow is about half as long as my first arrow. It's going to come back to bite me because I'm going to run out of room with my 100-meter long arrow, and which is supposed to be twice as long as the 40. Okay, so then my last arrow is 100 meters. Right, so when those things happen, I draw it like I'm telling a story. First they went 40, then they went 20, then they went 100. How far did they go?
160 meters north.
Right, their displacement is 160 meters north. Okay, so done. Okay, what's their distance traveled? Also 160 meters. No north on that one. Distance is scalar. Okay, that's how far they went. If you go in a straight line and you don't change directions, your distance and your displacement are going to be equal. Okay, it's when you start changing direction that they won't be. Everybody okay with that so far? Okay. So question number 2, okay, we've got this basketball player and they're going to perform a give and go. So what they do is they fake out the defense by moving 0.75 meters to the right and then 3.5 meters to the left. What's the player's displacement from the starting position? Okay, so start out. I'm just going to put a point here to represent the starting position of the basketball player. And they're going to move 0.75 meters to the right. And then they're going to go 3.5 meters to the left. Okay, can I find their displacement? Okay, that would be the diagrammatical version of it, okay? But could I also do this? Mathematically, is that the same thing as what I drew in the diagram? I'm going to get the same answer, right? Okay, that they're going to be 2.75 meters to the left. Okay, that will be their total displacement, right? Because they started here, that's their initial position. This is their final position, and that's 2.75 meters to the left of where they started. Right? So in that question, my displacement would be 2.75 meters left. What's the distance traveled in that question?
4.25 meters.
And that's it, right? 4.25 meters, right? I went 0.75 meters, and then I went 3.5 meters. Distance is scalar, it just keeps getting bigger. Okay, to do that, you had to travel 4.25 meters. Everyone following the difference there? Okay. So similar thing here, okay, with the bricklayer, sweeping the cement back and forth. Probably not something many of you seen because nobody builds anything like this anymore, but back in the day when you laid bricks like that cinder block wall there, okay, you'd lay the brick and then you'd put mortar on top of it and go down in the holes, okay, and then you put the next brick on top and squish it on there, and the concrete would go up into the holes of that one, and then you'd have concrete in the holes of the one below, concrete in the ones above, and it would stick them together, make them all one, like one big piece of stone. Okay, so what this person is doing is they're just starting here, and they're going over and back as they spread out the concrete. Okay, so they go. She swings her hand back and forth a distance of 1.7 meters 4 times. calculate the distance and the displacement her hand travels during that time. So it's back and forth 4 times. So if I start here, back and forth, back and forth, back and forth, back and forth. What's my displacement? 0. I ended up right back where I started. Okay? Sometimes it's easier to visualize that than to draw arrows doing this, 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 and on top of each other and then ending up back at the same spot. Okay? Now, if I want to know how far does she go in total, what do I have to do with this number? Multiply by 4. Okay? Everybody all right with that? Okay, so that's just vector, scalar, comparison kind of questions. Okay. I would like you guys to try question number 4 right now. Okay? It's not like mathematically challenging, it's to illustrate the importance of one thing. Okay? So I want you guys to try and draw that seating plan using those directions. What's tricky about that question? Like when you read the first one, Chad is 2 meters left of Dolores. How do you know where to put them? The answer is you don't really. Okay? You kind of probably just drew them and then drew everybody else using them. Okay? So the purpose of this question is to show you the importance of having a reference point. Okay? Before you start drawing out a vector situation or a vector diagram. Okay? The reference point in this question is Dolores. We don't know where she is. We know Chad is 2 meters to the left of her. So what you have to do in this question is you just kind of have to say, I'm going to mark my initial position as Dolores. And then I'm going to put Chad 2 meters to the left of her. Chad, that's not going to start with that letter. Okay, and then Ed is 4.5 meters right of Chad, which means he's 2.5 meters right of Dolores. Okay, Greg is 7.5 meters left of Chad. Okay, and Hannah is 1 meter right of Ed. Okay, well now I've got all the people in my seating plan drawn out, but I use Dolores as my initial position or my reference point to place everybody else. Now, part E says, make this your reference point and tell me what the displacement would be of someone who walks, or sorry, this is my initial point, who walks from Greg to Hannah. Okay, well 7.5, 9.5, 12, 13 meters. 13 meters to the right would be my displacement. Okay, so not that that question is like terribly challenging, it's just there to tell you if you're going to have a starting point, you have to use something as a reference. Okay, you have to know where to put that. Even if it's just, I'm going to put it in the middle because I don't really know anything else. And then I'm going to go from that point. Everything else will be measured from that point and I'll go from there. Okay? Reference points are important when we're talking about vectors. Okay? Question number 5 kind of illustrates that as well. Okay? A person's displacement is 50 kilometers west. What is his final position if he started at 5 kilometers east? Okay, so in this question, I know the displacement, 50 kilometers west. I know the initial position, okay, 5 kilometers east. Okay, I'm looking for my final position. Well, the 5 kilometers east is going to be my reference point because that's where he started. Okay, how can I solve this one? Can I use that formula from Science 10? Displacement is change in position, right? I know the initial position. I know the displacement. I just need the final position. So I'm just going to add the initial position over to this side. What's the only thing I need to watch out for?
Positives and negatives.
Positives and negatives. West, I'm going to make negative. East, I'm going to make positive. Okay, so what I'm going to have here is I'm going to add initial position over here, right? My displacement plus my initial position should equal my final position, right? Displacement's how much I change my position by. If I add that to my initial position, I should have my final position. Okay, so I'm going to have negative 50, okay, plus 5. Okay, well that's going to give me negative 45 meters, or 45 meters west. That would be my final position. Okay, if I started 5 kilometers east of something, okay, and then I went 50 kilometers west, I should be 45 kilometers west of that initial reference point. Okay, I want you guys to try question number 6. Okay, it's not terribly challenging, but there's something sometimes people forget if they don't read it carefully. Thank you. Yeah, so initial position right here, final position right here, okay, that's 5 basically minus 0, so 5 meters to the right, but for the total distance it goes 3 meters, and then it goes 8 meters after that. People just forget that that 3 meter section is covered twice because they just don't read it carefully. Okay, we're going to go over lots of questions where little details in a question can be the thing that makes you do it right or do it wrong, even though you totally could have done it had you just noticed that little thing. It's not so much a test of your math ability, it's more of like a reading comp kind of thing. And the reason we're doing that is the physics diploma is moving more and more towards lots of reading. Okay, we actually had a question a few years back where it was like a page, full page of text to answer one question. Okay, and like we read it over 3 times before we answered the question because there was so much there that didn't matter. Okay, it was basically a reading comp question. It felt like reading an English test. Okay, questions on any of those? Okay. Now, using B equals D over T, just quick to remember this. You're going to have tons of formulas. When I hand out your formula sheet, okay, there are lots of formulas on it, okay, and you have to be able to do real algebra, okay. Triangles are not going to cut it here, okay. They just won't work, okay, for our more complex formulas, okay. So when we're doing this here, okay, I don't know why I have meters per second underneath there. That's totally not right, but. So when we're using this formula, right, we have meters on the top for our distance, we have time in seconds on the bottom. When we divide distance by time or displacement by time, we're going to get meters per second, the units for velocity. Okay, if I want to manipulate that equation, I just follow those 3 basic rules of algebra. Okay, if I want to move something, I do the opposite. What I do to one side, I do to the other. And the third rule, the one people forget. Move what's not attached first. Okay, it doesn't apply in this one because everything's attached, but if you had this formula, and you wanted to solve for m, what should you move first? B. B is not attached to m, so you would move B first. Okay, so you would subtract B over to the other side, and then you would divide by x. Okay, just those little algebra rules, quick review, okay, so that we don't get stuck on any of that, because we will be using algebra every single day, okay, in this course. Okay, let's have you just try this one super quick. Just a V equals D over T problem, okay? Write down your givens, solve for the answer here.
Is the answer?
The answer's in bold, yes, just so you can check and see if you did it right. Okay.
Okay.
And on all your worksheets in your worksheet booklet, you'll see that the answer's in bold at the end. Yeah. This is one we would have done in Science 10. Okay, pretty straightforward. Okay, whenever you have a question in physics, a problem to solve, I want you to write down your givens, show me the formula you're going to use, manipulate that formula, solve for the answer. Okay, so in this one here, it tells us we have a speed of 67 meters per second, so we know that V equals 67 meters per second, and we're looking for how long is time. Okay, does it take for the Falcon to dive to the ground along a 150 meter path, meters measured distance? Okay, it did not say down, because it's probably diving at an angle. Okay, so it's not straight down. Right, so we don't have a direction here. All of these are scalar quantities. Okay, everyone with me so far? Okay, what formula am I going to use? V equals d over t. Yeah. Okay, that's what I've got. That's the only formula that has the things in it that I have and what I'm looking for, so I go with that. Okay, and I have to solve for t. Okay, well right now t is on the bottom. Can I solve for something if it's on the bottom? No. If I move the d, I'll be solving for 1 over t, which is not the same as t. It's the inverse of t. So what I'm going to do is multiply both sides by t. What am I going to do with v? Divide both sides by it. All right, so t is going to be d over v, 150 meters divided by 67 meters per second, and it should come out to 2.2 seconds. How did I know the units would be seconds?
Gives us time.
Because it's time. Okay, I can memorize that. The other thing I can do is go, when I divided these, the meters cancel, and I'd be left with seconds. Okay, everybody all right with that? Okay, let's try that one. It's a two-part question. Okay, the purpose of this question is to understand what average speed and average velocity actually mean. Do we need to make that bigger? Is that hard to read? It's okay? You guys all have young eyes. Okay, if you're getting 15.75, you did it right. This is just rounded to 2 significant digits. You may or may not have covered significant digits yet. It's something I'm going to cover tomorrow in our short class. Okay, so if you got 15.75 or whatever, I think it comes out something like that, yeah, you did it right. All right, so the importance of this question here is to illustrate what this formula actually means. Okay, we just write it like this, we don't think much about it, but what it actually means is that the average speed is the total distance divided by the total time. Okay? If I want to calculate the average velocity the average speed over this trip, I don't just take 21 and 4.2 and add them together and divide by 2. Okay? Why not? Are those 2 parts of the trip equal parts of the trip? Well, if you add 21 and 4.2 together, you're saying they are. Okay? Like if I calculate a class average for you guys in here, each one of you represents an equal part of the class. So I add all your scores together and divide by the number of you. Okay? You all represent an equal portion. I can do it that way when that's true. But in this trip, they went 11 kilometers at one speed and only 1 kilometer at the other. Okay? That makes one part of the trip way more of the trip than the other. Okay? It would be like saying I drove to Edmonton and the first 365 kilometers I traveled at 110, and then the last kilometer there was construction, I drove at 50, so my average speed is like 70 kilometers an hour. Is that true? No, my average speed is like 108 kilometers per hour. It was only the last kilometer where I had to slow down. Okay, that doesn't suddenly cut my average speed in half. Okay, I have to weight the average. Okay, and that's what we do when we do it this way. When we take the total distance and divide by the total time, we get the true average for the whole trip. Okay, everybody all right with that? So what we end up having to do is break this up into the 2 parts. Okay, so in part 1, I know that the distance is 11,000 meters. Okay, and I know that the speed is 21 meters per second. How did I know to convert that to meters?
1,000 meters to 1 kilometer.
Okay, that's how I did it. Why did I know I had to do it?
Is meters per second.
Yeah, if my speed is given to me in meters per second, my units for distance have to be the same. If I had meters per second in my speed, then my distance unit need to be meters. Otherwise, I'm dividing apples by oranges. Okay, the units always have to match. All right, so that's part 1. In part 2 of the trip, okay, the total distance there is 1,000 meters, and the speed is 4.2 meters per second. Okay, so if I want to calculate the average speed, I need the total distance and the total time. Can I get the total distance right now? Yeah, I know 1,000 meters, I know 11,000 meters, so my total distance is 12,000 meters. What do I not have?
The time.
The time. Can I figure out how long each part took? I sure can. Okay, I know this formula here. Can I use this formula to get time for each part? Absolutely. Okay, so we'll have 11,000, okay, divided by 21. I think that comes out to what, 523 or something like that? I'll just use the calculator. I shouldn't do things in my head. Or maybe I should. 523, that's not a 3. That's a 3.8. And I'll keep all those other decimals in my calculator. I'm just not going to write them all. Okay, seconds there. And then same thing here. T equals D over V. That'll be 1,000 meters divided by 4.2. Okay, Okay, so that's 238.1 seconds. Okay, now I can get the total time. Just add those two together. Okay, so plus that is going to give me 761.9 seconds. Okay, and then I just do the calculation. Okay, and when you do this, always carry all of your decimals. Okay, when you're doing all of this in your calculator, keep them all. Okay, because that's how we do significant digits. All right, so we get 15.75, but I round that to 16 because that number has two significant digits, that number has two significant digits, that number has two significant digits. So my answer can only have two significant digits. Okay, we'll talk more about significant digits tomorrow. It's pretty simple. Okay, so the average speed over the whole trip was 16 meters per second. Okay, all right. Okay, without using the graph, ignore the part here about the graph. Okay, see if you guys can solve this one. It's similar to what we did, but it's a bit more involved. You might have to work backwards a little bit. Okay, break it up into its parts. Okay, it's eventually, and at a couple of points, going to use v equals d over t as well as the whole total distance over total time thing. Okay, read it carefully. Okay, don't worry about the position time graph. Okay, so don't worry about part A. We're trying to solve for part B there. Okay, just in case you're kind of stuck getting it started, okay, put your givens in something like this, okay? Put what you know for part 1, put in what you know for part 2, okay? Put in what you know for part 3 and the totals. Okay, for the total trip, we know the average speed, it actually says velocity, but it means speed, is 40, oh, it actually gives you the direction too. So 40 kilometers per hour north, and it also tells you the total trip is 60 kilometers. Okay, can I leave them in kilometers here?
Yeah.
I can, because my speed's in kilometers per hour, so I can leave my distances in kilometers, the units already match. Okay, so it says that the car moves with a constant velocity of 25 kilometers per hour due north for the first part. Okay, and that is 15 kilometers. Okay, and then in part 2, it goes at 62 kilometers per hour. For 32 kilometers. And we know that the last segment is 13 kilometers long. Okay, you're trying to find that. Okay, think about what you need in order to get there and where you can get it from. You're probably going to do the same calculation a few times on different parts of the question, in case you're stuck. So what I've got to ask myself when I look at this question, now that I've got all my data written out, is if I want to get V for part 3, what am I missing in part 3?
Time.
Time. Yeah, I got to have the time here. Okay? I don't know what it is. In fact, it doesn't appear as though I know it for any of the sections. But part 3 is the only section I can't get it for yet. Can I calculate it in every other part? I can, because I have V and D in all the other parts. Okay, so I can simply manipulate this and go T equals D over V. Okay, have 25 over 15, so that'll be kilometers. Okay, over 20 over 15. Oops, sorry, I got that backwards. The 15 goes on the top. Okay, 15 kilometers divided by 25 kilometers per hour. The kilometers will cancel. I think that comes out to 0.6 hours. Okay, I do the same thing here. T equals d over v. Right, so that's going to be 32 divided by 62. This will be kilometers. This will be kilometers per hour. The kilometers will cancel. I'll be left with hours. So 32 divided by 62, okay, is 0.516 hours. Okay, and I can also get it for the whole trip, can't I? All right, so T equals d over v, once again, 60 over 40, that's kilometers per hour. Kilometers will cancel, and this trip takes 1.5 hours in total. So if I know now how long the whole trip takes, and I know how long 2 out of the 3 sections take, can I find out how long the last section takes? Is this a lot of like kind of, hoops to go through to get to the final answer? More and more questions are being designed that way. Jump through these hoops in order to see if you can connect the dots and get to the final picture. Okay, so if I want to get the time here, that's going to mean going 1.5 minus 0.6 plus, and minus 0.516. Okay, so I punch all that in, so I have 1.5 minus that number, minus 0.6. Okay, so what's left is 0.383 hours, or 0.384 hours. Okay, well, now I've got d and t. V equals d over t, 13 divided by that 0.384. Okay, and I'll have my final answer there of 34 kilometers per hour. Okay, everybody all right with that? Okay, so just illustrating, remember that V equals d over t actually means average V is total d divided by total t. Okay, that way it can be used over a many part trip. All right. So you guys are going to find the question I was actually looking for here. It's not there. Okay, I'm going to give you guys about a 5-minute break and we're going to start talking about how to do vector addition here. Okay, pretty simple today. It's just going to be kind of the conventions and rules around drawing everything. Okay, but that's what we'll start out with today. So I'll give you about a 5-minute break here. Right? And what we're going to look at now is kind of taking another step beyond what we did in Science 10 with vectors. Okay, I already showed you how we typically draw vectors, where we use arrows to represent vector quantities. Okay, length of the arrow represents the magnitude of that vector quantity. The direction the arrow points represents the direction of the vector. Okay, so it's pretty simple to represent vector quantities in physics. We just draw a lot of arrows pointing in different directions. Okay, it's how we draw them that's kind of important, because if we don't follow scale and things like that, our diagrams can lie to us, okay, later on, and we don't want that. All right, so we're going to look at the different kinds of vectors. We'll start out with the ones we're familiar with. We call them collinear, or one-dimensional. That would be right and left, north and south. They are on the same line. They share that line, collinear. Okay, we'll also look at perpendicular. We haven't done any of those yet. Okay, that would be where one vector goes east and the other goes south. Okay, they're 90 degrees from each other, and they would make a right-angled triangle. We bring trigonometry into something like that. That's where we're going to go today, and that's probably about as far as we will get. Okay, so things we need to know. What are collinear vectors? They share a line. All vectors are added by placing them tail to head. Okay, so that orientation is important. Okay, all types of vectors are added by placing them tail to head. As I did when I showed you that very first question where they ran 40 meters, then they ran 20 meters, and then they ran 100 meters. I just drew the first one, I drew the next one on the head of the first, I drew the third one on the head of the second, like I was telling a story. First this one happened, then this one happened, then this one happened. That's how we draw our vectors, because they end up telling us a visual story of what went on in that problem. Okay? So we need to understand that vector quantities obviously have magnitude and direction, which we already know, okay? And that all vector quantities are added the same way. It doesn't matter whether it's a displacement vector, which is what we use most often, a velocity vector, an acceleration vector, a force vector. They're all added tail to head. We all treat them all the same. Their magnitude is their length. The way they point is their direction, okay? All right, so simple situation here, okay? Here's our first vector, okay? This vector is 2 kilometers in length, and it points 30 degrees north of east. Why do I say it like that? Why do I say it north of east rather than northeast?
Because if you look, the angle is 30 degrees directly up from east, so if you run straight east and then you go 30 degrees north of that, that's where you're going.
Right, and could there be another 30 degrees northeast?
East, north.
It would be east of north though, okay? It would be not this 30 degrees, it would be that 30 degrees. That's 30 degrees east of north. That angle is measured from north, not from east. Okay, so when I say north of east, I'm saying this angle was measured from east, not from north. Everyone follow the difference there? Okay, so when I'm saying north of east, I'm saying draw the triangle with east on the bottom and go up from there. If I'm saying it's east of north, I'm saying start at the top and go east from there. Okay, we say them differently because they are different. If I say northeast, well, there's 89 northeast angles. Anything between north and east is technically northeast. That's not very specific. Okay, so we say it's this many degrees east of north or this many degrees north of east. Okay, I could also say that this angle was 60 degrees east of north. Okay, and that would be absolutely correct as well.
For, like, if it was a 45-degree angle, would you have to specify whether it was northeast or east or north, or would that be like the one case acceptable to say northeast?
You would still have to specify.
Okay.
Both would be right, of course.
Okay.
But yes, you would have to say east of north or north of east. They would both be right, but you would still have to put that in there. Yeah. Okay, so the big thing from this slide is the first convention of drawing vectors. The direction the arrow gives the direction of the vector. Okay, whatever direction I draw the arrow, that's the direction the vector is going. In this case, 30 degrees north of east. Okay, now that also means you got to get your head around compass directions. We use them a lot. Okay, so if you're ever lost, just draw compass rose. I still do it sometimes when I draw vector addition. Okay. Okay, compass rose goes like that. Okay, and what lots of people do, and I still do it from time to time, if the question says it's 40 degrees south of west, I'll put my pen on west. I'll go 40 degrees. Boom. There's my vector. It just helps me with a reference to know where to draw that line at. Okay, and then I can put it in my diagram after that. Okay, but it gives me a handle on where does this thing need to point. Okay. All right, so everybody okay with that? The direction the arrow points represents the direction the vector is going. Okay, and the second part of it is the length of the line is proportional to the magnitude of the vector. Okay, it is important that we always keep scale in mind when we're drawing these. You don't have to measure it, but it should be close. Okay, so here's why I say that these two things are really important and why scale has to be kept in mind. Let's say I have a question that says your first vector is 10 meters long due east. Okay, that would be a 10 meter long vector pointing due east. All right, and then the second part says then the object turns and goes 10 degrees east of north for 2 kilometers. Okay, well, if I just do this and kind of go, okay, 2 kilometers, 10 degrees, all right, and draw that, is that going to give me an accurate idea of what's going on? That line is, like, by scale, probably closer to 6 or 7 meters long, and that's definitely more than 10 degrees east of north. So when I'm done my calculations, I'm going to do all this math, I'm going to look at my picture and go, well, that's not what my picture says. Okay? And unfortunately, okay, because we've been kind of ingrained this way, we're like, drawing's easy. So I must have messed up the math, because there's no way I would have drawn it wrong. Drawing's easy. Actually, what messes most people up on these kind of questions is they draw it wrong. Okay? Their math is totally fine, but they don't believe their math. They look back at their picture and go, no, I must have screwed up the math. Okay? No, draw the picture, but draw it carefully. If I was really drawing that carefully, okay, oh, that's not what I want. Okay, I would have, okay, fine, do it that way then. Okay, I would have done this. I would have gone, okay, here's north. This would be about 10 degrees east of north, and that would be more like 2 kilometers. Okay, that's going to give me a much more accurate representation of what my question was telling me, because that diagram, I worried more about the scale. Did I measure everything? No. I don't have to. It doesn't have to be that exact. It just needs to be at least somewhat to scale. Okay? Okay, so the easiest kind of vector addition questions are the kind we've already done. Okay, so in this slide here, we've got 2 vectors. The first vector says that the car moves 275 meters due east. Okay, so that's this first arrow here. Okay, 275 meters, and that's east. Okay, then the car goes another 125 meters due east. So I draw that vector, put its tail on the head of the first. I'm drawing them tail to head. I'm telling a story. This one happened first, then this one happened. It's 125 meters long. It's also due east. What's my total displacement? $400 meters due east. Okay, I'm just drawing those 2 things, tail to head, and getting my answer. This plus that. Now, what if the question had instead not said it's going due east, but instead said it turns and goes due west 125 meters? Now what do?
Subtract.
Yeah, well, I still draw it this way though, right? But mathematically, yes, I will subtract. I'll go, all right. Okay, here was my initial position. Here's my final position. Okay, 275 minus 125. Okay, should give me 150. Right? Okay, meters. Still which direction? East. That's why the diagram is important. At the end, the diagram can help you with the direction. I went east, then I went west, but I didn't go as far west as I went east. So I still ended up east of where I started. Okay, that's what the diagram can help you with. Okay. All right, everybody okay with the simple one, the collinear one? Okay, we just draw them tail to head. Doesn't matter how complex they get. Doesn't matter how many vectors you get. Okay, I'm actually at one point going to give you a 5-vector question with angles. Okay, all you do is just keep drawing the next one on the head of the one before it, and by the end you have a picture. Okay, and you know what's going on. It's not going to make anything cool. It's just going to be a track. But okay, so that's what we did. Okay, tail to head. Okay, all vector addition is done in that manner. It doesn't matter what kind of vector quantity it is. Displacement, velocity, acceleration, force. As it's a vector quantity, it gets drawn like that. The only thing that changes is at the end, instead of meters, you've got meters per second squared, or newtons, okay? But the rest of it is all the same. Okay, anybody need that one anymore? All right. Trig's going to come into play starting right now. So now, same car, but now that first vector, okay, is still 275 meters due east. Okay, but now instead of continuing east, the car turns north. Right? So the second vector still gets drawn tail to head on the first, but now it points due north. Okay. My displacement is now the red line. How do I get that?
A squared plus b squared plus c squared.
Right, use the Greek geek, okay? Pythagoras spent his whole life studying triangles, okay? He's the Greek geek, Pythagoras, okay? Now, if I want to get this, then I'm going to go, yeah, a squared plus b squared. That'll get me the what of this line? Starts with M. Magnitude. It'll give me the magnitude of this line. What else do I need since that's a displacement? I need the direction. Okay? I'm going to have to solve now, not just for the length of this line, but also for theta. That will be the direction that that vector quantity, in this case displacement, is pointing. All right, so sure, the a squared plus b squared part, that's going to be easy. I'm just going to say displacement is going to equal 275 squared plus 125 squared. Okay, so 275 squared plus 125 squared. Okay, so that side's going to be 302 meters in length. Okay, now I know all three sides of that triangle. I want to find theta. How do I go about doing that?
It's a secretary, you have to do the angle times the hypotenuse is equal to one of the sides, the side opposite of the missing angle.
Right. In fact, at this point, because I know all three sides, I could use any of those trig functions. I could use sine, cos, or tan. Okay? I know the opposite side, the adjacent side, and the hypotenuse. So pick your favorite. Okay? Any of them will work. My favorite is tan. I don't know why, but I like tan. Okay? So for me, I'm going to solve for theta using tan. And I know that tan equals, okay, sorry, the tan of theta equals the opposite side over the adjacent side. So for me, since the angle is here, the opposite side for me is 125. The adjacent side is 275. Okay? And all I have to do to get theta is go inverse tan. Okay? So I would have then tan to the minus 1 of 125 divided by 275 equals theta. What mode does your calculator have to be in for this? Degree. Okay? So if you're in math right now, you're probably going to be jumping back and forth between radians and degrees. When you're in physics, it always needs to be in degree mode. Okay? Otherwise, you're going to get a lot of strange answers. All right, so I'm just going to go second tan, okay, of 125 divided by 275. Okay, so the direction, according to what I've done, that the car is going is going to be 24.4 degrees. Which direction is it? Okay, yeah. Which direction is it? North of east. Okay. Now, how do I know that? Well, because my angle arc that I drew is touching east and going north of it. Okay. So what I always say is, if you need like a rule or a tip to help you, is draw that angle arc, and whatever main compass direction it touches, it's of that. Okay, it's touching east, it's something of east. In this case, north of east. Okay, would it be fair to also say 35.6 degrees east of north? Sorry, not 35, 65.6. Okay, fair? That adds up to 90, I think, in my head. Okay, it would be fair. That's also the same direction, it's just measured from the other main compass direction. Okay, is that very hard? It just brings a little bit of, you got to remember your SOHCAHTOA, right? Sine is opposite over hypotenuse, cos is adjacent over hypotenuse, tan is opposite over adjacent. Okay, just got to remember that. Okay, you can't go wrong from there. You're not gonna have to do any sine law, okay, or anything like that. In fact, don't. If you know how to do sine law, good for you. Keep that in your back pocket and never use it in physics. Okay, here's why. If you mess it up, you'll have nothing to go back to know whether you messed it up or not. Okay, I can't help you. If I look and you've just got sine law written down on your paper, I'm gonna look at that and go, I don't know, how did you get that? Okay, I don't have a diagram to go back to, I don't know where you got those numbers from, okay, and I can't help you. If we want to be able to break this down and look at it piece by piece. As we get into other questions, it won't just be, what's the final answer? To it's, here's the final answer, work backward and find one of the parts. Sine law won't do that for you. Okay. Okay, so we did all of that. Okay, we did that. All right. Okay. Write this question down, give it a try. This is a race in the world's most boring town. Okay, when you read the question, you'll understand why I say it. Okay, in this question, what kind of vectors are we dealing with? Perpendicular or collinear? Do they all go the same direction? They're all forward, right? Okay, that means they're collinear. They're all on the same line. Collinear vectors all point the same way. Okay, so this is the easiest kind of vector question. Okay, so these contestants move forward 10 meters and then untie some knots. Okay, like I said, this is the world's most boring town. Okay, so 10 that's a 10. Okay, 10 meters. Then they go 5 meters and solve a puzzle. Okay, not great scale there. The 10 should probably be just a little longer, but I'll do that. Okay, and then lastly, they go 25 meters to the finish line. Okay, so I wasn't super careful about my scale. I did adjust one of those lines just so that the scale was a bit more accurate. Okay, does that generally show what happened in that race? Okay, what's their total displacement? 40 meters forward. Yeah, that's the direction the question gives us. Forward, that's the direction our answer has. 40 meters forward. Okay, about as simple as they get in terms of drawing tail to head vector diagrams. Okay, questions on that one? Okay. All right. I want you guys to try question number 7. It's a bit of an algebra trick, but it's also valuable to draw the picture as much as you can, okay, in order to kind of get you going on it. So in this trick, all we know right now is that the car drives 500 kilometers north. Okay, so this is its initial position right here. Okay, we know it's going to drive back, okay, and that each sequence of that trip back is going to be 50 kilometers. Okay, the final position is 50 kilometers north of where they started. Okay, so if this was the initial position here, okay, then the final position is going to be basically here, coming straight back. Okay, that trip will consist of 3 parts. Okay, each one, okay, is going to be 50 kilometers longer than the first one, which we have no idea how long it is. Okay, this is where the algebra trick comes in. Okay, what's going to be the overall displacement if the final position is 50 meters north? How far is this?
450 meters.
Okay, so I know that last part is 450 kilometers in total. Okay, and I know that 3 parts add up to that. I don't know how long the first part is, but that's okay. I'm just going to write that it's x. Okay, how long is the second part? $50 kilometers longer than that. Would that be x plus 50? Okay, so the second part, so I'm going to have x, and then I'm going to have x plus 50, and then I'm gonna have, I didn't draw this to scale very well, x plus 100. Okay, if each one is 50 kilometers longer than the one before it, that's how that should arrange itself at the end. Okay, so I'm going to have an equation that goes x, okay, plus x plus 50 plus x plus 100. It's an algebra trick. How many x's are on that side? 3. So could I also say then that 450 meters, or kilometers, sorry, equals 3x plus 150 meters? Would that be fair? Okay, can I subtract 150 meters over to the other side? Okay, would that leave me with 3x? Okay, so 450 minus 150 is 300 kilometers equals 3x. How long was the first length? 100 kilometers. Okay, so find the three displacements algebraically. Okay, 100. Okay, 150, 200. Okay, that's all we have to do for that. Okay, it seems really like convoluted when you first read it, but once you start writing it and drawing that picture, having those tail to head ways to look at it, it helps you to figure out where to go with the algebra after that. Okay, am I ever going to give you one like that on a test? No, that's more of an algebra trick than it is a vector question, but it allows us to see how can the vector diagram help us get somewhere. Okay, we're going to leave it there for today. Good job. Don't forget your phones on the way out, guys.